All right, showing that a function is onto. This is the alternative approach. Now, to show that a function is onto, we must show that for every element in the codomain, there exists an element in the domain which maps to it. We can prove that a function is onto either algebraically or graphically. So we just looked at the graphical approach. Now, the algebraic proof. This says, let Y be an element in the codomain and X an element in the domain. We solve the equation Y is equal to f of X for X. In other words, we're going to start out with Y is equal to f of X, and we are going to change the subject of the formula and make X the subject. All right, and our objective is to show that for every element X in the codomain, there exists an element, for every element Y in the codomain, there exists an element X in the codomain that is mapped to it. All right, let's have a go at example 13. All right, so example 13 is asking us to prove that the function f defined by f of x is equal to 7 x minus 2, where the domain elements and the codomain elements are both real numbers. And to prove that a function is onto, we have to show that every element in the codomain y is the image of at least one element in the domain X. So the way we're told to do this is to make Y, so Y is equal to f of X, make Y an element in the what? Codomain. So Y is equal to 7x minus 2. Then we need to make x the subject. So y plus 2 is equal to 7x. If I divide both sides by 7, I'm going to get that x is equal to y plus 2 over 7. So here is something. Remember, if y is an element of the set of real numbers, x is also an element of the set of real numbers. So that's the first thing. If y is a real number and x is equal to y plus 2 divided by 7, and y is a real number, any value of y I choose, I will always get a corresponding value of what? X. Every value of y being an element of the set of real number that I select, using the formula x is equal to y plus 2 over 7, I will always get a corresponding value of x. I can also show that f of x, which is the same as saying f of y plus 2 over 7 is equal to 7 times y plus 2 over 7 minus 2, over 7 over 7 minus 2. The 7 cancels 7. So I'm going to end up with y plus 2 minus 2. 2 minus 2 is 0. So I'm going to end up with what? Y. So we've already seen that if x is equal to y plus 2 over 7 and y is a real number, x must also be a real number. And that for every element x, where x is equal to y plus 2 over 7, there exists an element y in the what? In the codomain. We have shown that. So therefore we can say for all y in the codomain of f, there is a corresponding value x in the domain. Therefore, f of x is onto. So that is the calculation approach. All right, so let's have a look at the alternative approach. Now, for the alternative approach, we have to draw a sketch of the graph of the function f of x is equal to 7x minus 2. Again, this is a linear function, and the graph of a linear function is a straight line. So I'm doing a sketch, so that's my y-axis. Then my x-axis. This graph cuts the y-axis at minus 2. Minus 2 is the y-intercept. It has a positive gradient. It's a very high gradient. Gradient is 8 and it is positive. So my graph could look something like this. Again, remember, the graph actually goes on forever in both directions. So this is a sketch of the graph of f of x is equal to 7x minus 2. We're told that in order for the graph to be, in order for the function to be onto, every horizontal line that can be drawn must cut the graph at least once. So let's draw a horizontal line. All right, and we can see that this horizontal line cuts the graph one time. So the qualification is that it must cut it at least once, meaning that if it cuts it one time, it is onto. If it cuts it more than one time, it is still onto. So I can make my comment that every horizontal line, if every line drawn parallel to the y-axis will cut the graph of f of x is equal to 7x minus 2 at least once. Therefore, f of x is equal to 7x minus 2 is onto.